Welcome to the lecture on organic chemistry. We've just finished learning how to name compounds that are formed by inorganic, well, partially by inorganic elements, those elements that are not carbon, that would contain a metal and a nonmetal, so ionic compounds. And then we also learned how to name some simple covalently bonded molecules that may or may not contain carbon. We are going to now, because this class is about organic and biological chemistry, in addition to inorganic chemistry, we're going to learn how to name some simple organic compounds. Organic meaning the chemistry of carbon. So on this next slide, I have pictured here, just by way of example, three molecules that represent the huge variety of compounds that carbon can make, because carbon can bond with itself in many different forms and with other elements as well. This first compound up here, glucose, has not just carbon and hydrogen, hydrogen being the white balls, the white atoms, and oxygen being the red ones. Carbon, hydrogen, and oxygen, C6H12O6, the energy molecule for most life. We are burning glucose in order to form ATP, which is the energy, other energy molecule that we use to run our biological processes. Underneath glucose, the simple sugar glucose, 6-carbon sugar, we have ascorbic acid or vitamin C, another carbon, hydrogen, oxygen compound. They are very similar, these two compounds, in that they contain many oxygens on the edges of the molecule. This is going to affect the physical properties like dissolving and so on. Both of these compounds dissolve very well in water because they are polar with all of these oxygen groups, which have high electronegativities, on the edges of the molecule, and therefore they're going to dissolve in things like water. In contrast, we have a carbon, hydrogen, many carbon hydrogens with just a couple little oxygens on the end. This is stearate or stearic acid. It's stearic acid without a hydrogen. It's fatty acid. And your fats are made up of fatty acids. In fact, triglycerides are made up of 3 of these fatty acids. That's what the tri means. So this is one of the fatty acids, and you notice that there's lots of carbons and hydrogens, which means that it's pretty unpolar or nonpolar. Nonpolar. Carbon and hydrogen only, you're going to be nonpolar. Little bit of polarity here at the end, which enables fats to dissolve in water if you have something around like a detergent to help in that process. But anyway, these 3 molecules are pictured here just to give an idea of the diversity that is capable when you are talking about carbon bonding with itself. It can form long chains. As you see here, it can form much longer chains than those. There are even larger biomolecules like proteins and lipids. Glucose would be a carbohydrate, and nucleic acids are all carbon-based compounds. The structure of carbon is easiest to understand in terms of if you hear the nomenclature and the way that it's discussed by looking at the geometry around a carbon atom being central in, you have, in fact, if you look back at these large biomolecules, you have many central carbon atoms. And the geometry of every one of these carbon atoms is different depending on the types of bonds. So if you look at the stearate here, you have all single bonds are with these carbon atoms. So this is going to be like the first one we're talking about on the next slide. Here, you've got a carbon that has 2 singles and a double, so that'll be like another one of the types of carbon centers that you can have. Up here in glucose, it's all single bonds. So that is going to be like the first type on the left on the next slide. So when you have 4 single bonds and around carbon, then the geometry of that carbon atom is going to be tetrahedral, as we've learned in our discussion about VSEPR, valence shell electron pair repulsion theory. In order for carbon to be able to do that, it must hybridize into what is called sp3 hybrids. Just real quick, let's talk about, we didn't talk a lot about hybridization at all, in fact, not at all, but let's look at carbon's valence electron configuration. You really cannot understand what organic chemists and some of the things that are said about carbon unless you think about it this way. Carbon, the element, has 4 valence electrons in the second shell. So we learned that if I put in carbon's 4 valence electrons, it would be like this. Well, one thing we didn't talk about in our discussion when we did Lewis dot structures was that in order to form a covalent bond like this one, generally you have an electron from this atom, that's what we were depicting in those Lewis dot structures, and an electron from this atom. They share to make that dash. Remember, we called all the dashes 2 electrons. Well, according to this electron configuration for carbon's valence shell, it should really only be able to make 2 bonds, because here are 2 unpaired electrons that can be shared with another atom that also has an unpaired electron. So what this sp3 hybridization means is that you take these electrons in the s orbital and the ones in the p, and you mix them up so that now you have 4 equivalent, and then take those 4 electrons, and now you have 4 equivalent orbitals with 1 electron each, and that's why carbon is so good at forming 4 bonds. All right. If you have this type of carbon center, like we saw in the ascorbic acid, there was an example of carbon with 2 singles and a double. Double and triple bonds, which here's one here, a triple. Double and triple bonds involve this kind of arrangement, and then you have to have an unhybridized P. Unhybridized P. You need 1 of those in double bonds, and you need 2 in a triple bond. So let's go back to this situation here. We have 4 equivalent bonds, and we call these bonds that are single bonds, we call them sigma bonds. So in when a carbon atom has 4 single bonds to it, it's sp3 hybridized, they're all sigma. When it has 2 single bonds and a double, this double bond is both 1 sigma and 1 pi, and it's the pi bond that is the unhybridized P. So for something like this with the double and 2 singles, I am going to take the S's and the P's from carbon's ground state, and I am going to do the S and 2 of the P's so that I have 3 equivalent orbitals, each with a single electron, to do this sigma bond, and this one. And then the unhybridized P that's out here is the other. Same thing's going on with oxygen, and we form what is called a pi bond. A pi bond is not, a sigma bond is end-to-end overlap between orbitals. That's what a sigma bond is. Orbital from this atom, orbital from the carbon, overlaps in along the nucleus between, not the nucleus, along the axis between the 2 atoms. Here's the carbon, here's the hydrogen, and it's end-to-end overlap. P orbitals, if you remember, are shaped like this. So if you've done nothing to change that p orbital, then it is a p orbital on one atom and a p orbital on the other, where the sharing is between these lobes, and that is a very different kind of bond. So in a double bond, you got a sigma and a pi, and in a triple bond, you got a sigma and 2 pi's. So you only need 1, 2 sigma bonds in a carbon atom that has a triple bond and a single bond. Oops, sorry about that. All right. But other hydrocarbons are alkenes, named very similarly to alkanes, alkynes, and then aromatic hydrocarbons. So, alkanes, only these hydrocarbons means only carbon and hydrogen. All four of these only contain carbon and hydrogen. Alkanes have only single bonds between all the carbon atoms, and of course, between carbon and hydrogen, you wouldn't have a double bond with a hydrogen. In an alkene, and these, one more thing I want to say about alkanes, these are called saturated hydrocarbons, meaning that they are saturated, that the carbon atoms are saturated with hydrogens. All the maximum number of hydrogens are there because you've got four single bonds. Alkenes and alkynes, as well as aromatic, are all unsaturated, meaning that they are not, you do not have the maximum number of hydrogens because some of the hydrogen positions, say these two, are now gone in order to form the double bond. So remember, let's review what we said in the previous slide. If I've got all single bonds, there's the bond angle that tells me we are sp3 hybridized because I've got all single bonds, all sigmas. When a double bond is present, I need one, two, and then one of those bonds in the double is a sigma. So I don't need four sigma bonds like in sp3. I only need three. So we are sp2 hybridized. The extra p that's not being mixed is used for the pi bond that is also present and makes it a double bond. In a alkyne, where I've got a triple bond, I only have two sigma bonds. I only need two orbitals to mix to form those sigmas. The other two unhybridized p orbitals are forming the two pi bonds that are present in a triple bond. And an aromatic hydrocarbon is a special animal. It is, you see a circle here because really what you have are alternating singles and double bonds, but because of resonance, something that we learned about in our discussion about Vesper, those double bonds move so much that you end up with circle of electron density from the pi bonds. Those pi bonds, those p orbitals are up above and below the plane of that six-membered ring, and that is the electron density that that circle is being designates, and that leads to reactivity. All three of these are more reactive than the alkanes. The alkanes have just carbon and hydrogen, not a whole lot there to react with. So once again, alkanes contain only single bonds. They are also known as saturated because they are saturated with hydrogen. So when you hear the word saturated fat, they are talking about a fat that only has single bonds and not double bonds. So when we look at the organic formulas, there are lots of different ways that we can look at them. We could look at them as Lewis structures, and that would be the example of which would be what's drawn right here. So this would be a Lewis structure for this alkane. That's not very convenient and takes a little while to do. So what is often done is you use this kind of formula, and the next slide identifies what we call those. They are called condensed formulas. Oops. Condensed formulas take a Lewis dot and take the bonds between the hydrogens and carbons especially, and instead of writing this, we write CH3. It's understood that these three hydrogens belong to this carbon. This bond that's there or not there, even in the case of this one, is between the two carbons. These two hydrogens are bonded to this carbon and are represented by this here in the Lewis dot and so on. So we go CH3, CH2, CH2, CH3. So this is a condensed way of writing a Lewis dot formula by not showing all the bonds. Properties of alkanes is if you've got only carbons and hydrogens, then the only intermolecular force that you would have between the molecules, and that's what intermolecular forces are all about, would be the London dispersion force. We haven't really talked about intermolecular forces, but these are all nonpolar molecules, so anything that's nonpolar has this weak attraction between molecules. Now, that weak attraction increases when the molecule gets bigger. So as our alkanes get larger and larger and larger, the boiling points of them increase because the force of attraction between the molecules has increased. Now, the thing to notice really here is that when I've got one carbon, my prefix is meth. If I have two, it's ETH, prop, but for 4, pent for 5, hex for 6, hept for 7, and so on. Octane is 8, nonane is 9, and decane is 10. So these are straight chain hydrocarbons made of only a carbon and hydrogen. They're all alkanes, of course. But these prefixes are going to be used throughout organic chemistry to designate the number of carbon atoms present. Now, we are only going to touch, on organic chemistry in a small way, but by learning how to name alkanes, we're learning so much about how to name all the rest of them because they're all based on alkanes. All the rest are named based on these same rules. So, one more time, alkanes means all single bonds. Oops. So that means that you have sp3 hybrids because it's all single. You need 4 single bonds, which means 4 sigma bonds, and your angle is going to be that same as it is for a tetrahedron. 4 bonds, no lone pairs. So you have the 109.5 degree bond angles. This is true in all alkanes. Because of that structure and the fact that you only have sigma bonds and things aren't locked in place like they are when you have a double bond. So when you have a double bond between carbons, this gives 4 electrons between the 2 carbon atoms, which kind of locks the molecule, or the 2 carbons are locked more into place because they're sharing more electrons. When you're only sharing 2, then you have rotation, as this diagram is trying to show, that this whole methyl group here, 1 carbon, this whole methyl group can turn relative to the rest of the molecule. So you get a lot of rotation. This is going to affect properties, but that's true because they're all single bonds. We are not going to talk a lot about isomers, but they are very important, and a lot of biological compounds have specific isomers that work in our biological systems while others don't. And what an isomer is that you have the same molecular formula, but you have a different bonding order. Now, there are geometric isomers, which is what this chart is trying to show, and then there are optical isomers and so on, but save that for more organic chemistry into a real organic chemistry course. So the C4H10 is the formula for butane, but I can put C4H10 into many different arrangements. That C4H10, that's 1, 2, 3, 4, that's also C4H10, but these are 2 completely different compounds with different physical properties. Not tremendous difference here. Here's a 5 carbon compound. Here's also a 5 carbon compound. A bit of a difference here because the difference in structure. And then here's another 5 carbon compound with a much bigger difference in structure. Now notice this. Notice that for these 3 5 carbon compounds, the one with the highest melting point is the straight chain one. These are all alkanes. They're all single bonds, all carbon hydrogen. Remember, it's only London dispersion, a weak intermolecular force. But when I am long and skinny, the next long and skinny molecule, I can get pretty close to each other. Okay, and that's where this force of attraction is between the molecules. Well, when I'm circular like this one, I can't get as close to the next, and so therefore my melting point and boiling point are going to be much lower, because the force of attraction doesn't take as much energy to separate things that can't get as close together. So when you're talking about, and this is one of the reasons why animal fats, which are unsaturated, straight chains of carbon, are solids at room temperature, like lard, whereas vegetable oils, which have double bonds in them, can't get as close together, and they have higher boiling points and melting points due to the presence of those double bonds. We are going to separate them into 3 basic parts: the prefix, the base, and the suffix. The base is dictated by that chart I was referring to before. So something with the base of meth is going to have one carbon. Another way of saying meth is formic. Formic acid only has one carbon atom. Um, Ethane has two carbons. So anything with A refers to alkane actually. So the suffix is the family, and for alkanes that is going to be ANE. If it has substituents, which means that first of all, everything we do in organic chemistry in terms of naming is to really look at the carbon chain, the basic carbon chain. So if it has 4 carbons, then bute is the base. If it's all single bonds, then it's butane. Now what if this butane had a chlorine atom bonded to one of the carbons? That's what the prefix is about. It's about substituents. That's what we call these other groups other than hydrogen that are bonded to the basic carbon chain. So we would say in the case of this one, it would be 1-chlorobutane, because I'm saying which carbon the chlorine is on. All right, and we are going to go through the rules for how to do this over the next few slides. So here is a typical type of molecule, and the first thing you want to do is find the longest chain. So it could, it depends on how you draw it. If it's got a kink in it like this does, then that doesn't matter. It's whether or not you have to pick your pen up to trace the chain. So it can have a kink in it, but I can trace that chain without picking up my pen, and it is 6 carbons long. If I had picked this, just left this whole group out and just picked this carbon chain, then it would only have 4 carbons on it. You want the longest continuous chain. So the longest continuous chain here has 6 carbons, so therefore its base is going to be hex. And the ending is going to be ane because it's an alkane, all single bonds. It has a substituent on it. It has a substituent right here, this one. And it is on the 2nd carbon. Yes, it matters which end you number the chain from. You want to number it where the first substituent has the lowest number. All right. So if I had started numbering at this end and called it 1, 2, 3, 4, 5, 6, then this would be 5-methyl hexane. Methyl is the name given to the substituent that has 1 carbon. Notice the meth base. If it has 2 carbons, it's ethyl and propyl and so on. But that's not correct. I don't want to name this 5-methyl hexane. I want to give that substituent the lowest number, so I am going to start numbering from the opposite end. So the correct name for this compound is 2-methyl hexane, because that gives me the longest continuous chain of 6 carbons, ane because it's an alkane, methyl because there's a 1-carbon substituent on the 2nd carbon of that chain. If you have more than one type of substituent, then you're going to list them alphabetically. So first of all, the longest continuous chain here has 7 carbons. All right, that means that this is a substituent, and so is this, and this, and this, because they are not part of that continual 7-carbon longest chain. So heptane is my base and my suffix, ane because it's all single bonds. Hept is 7 carbons. Now, the substituents. I have a methyl, a methyl, and a methyl, and an ethyl group. I want to number them so that they have the lowest numbers, okay, for substituents. So if I had started at the other end, 1, 2, 3, 4, 5, then my substituents would be 2, 5, 5, ethyl comes before methyl, so that's why it's first, 4 ethyl, we'll go back over this in a minute, 2, 5, 5, trimethyl, heptane. All right. Well, if you look at this name versus this one here has the lower numbers for the substituent, so that is why we start numbering at the other end. And literally, it's like trial and error, and you get used to it after a while. So, we had methyl groups and ethyl groups. If you have more than one type, to list them alphabetically. So the eth came before the meth. The tri had nothing to do with it. I needed to say tri so that it would be understood that at carbons 2 and at carbon and twice at carbon 5, well, better, 2, oh, my bad. They are not on the same carbon. It's 2, 4, 5. So by my other numbering system, was not correct. It'd be 1, 2, 3, 4, 5, 6, 7. So I did not do that right at all. Let's do it again. I want to make the point here about numbering from the correct end. This would have been called 5-ethyl 3, 4, 6, 3, 4, 6 trimethyl, and the rest is the same. So 5, 3, 4, and 6 is much higher than 3, 2, 4, and 5, so that's why the correct numbering is to start here. All right, so if you have more than one type of substituent, in this case we had ethyl and a methyl, the ethyl goes first because of alphabet. Even though I have a tri here, it's the M in methyl that I'm using to do the alphabetization. So here it is. Here are the rules again. Select the longest chain. Select the longest chain. Number so that the substituents have the lowest numbers. You want the lowest numbers for the substituents. There it is right there. Use di, tri, and tetra if you have multiples of a single type, and then arrange them in alphabetical order, but you don't use the di, the tri, or tetra in your alphabetization. You can have these carbon atoms, instead of in straight lines, they can be in rings. And we would name them similarly, except we would put cyclo as a prefix. So I have 6 carbons in this ring, so that's why it's hex. It's all single bonds, so that's why it's ane suffix. And the prefix is cyclo to indicate that it is in a ring. 1, 2, 3, 4, 5, so it would be pentane, cyclopentane, and then cyclopropane. This ring here, very uncommon because it's very strained. The carbons are very close to one another. The electrons are too close. What I've got here are a number of websites for practice, so we're going to go through some of those to get practice on this naming that we've just learned how to do. So let's go to this one first, because it has some non-line drawings, and I'll go back to helping you with that. So first, this is okay, alkane names. So it's just kind of walking you through it. Their alkanes have a general formula. This is important. So when I look at a formula, I know whether or not it's an alkane by the general formula. So if it's C2, then it should be 2 times 2 is 4 plus 2. There should be C2H6 if it's an alkane, meaning that you're saturated with carbons, with hydrogens rather. All right. If you're an alkene, it's CnH2n. You drop off the plus 2. And if it's an alkyne with a triple bond, then it is, I believe, CnHn. So if an alkane propane has 3 carbon atoms, how many hydrogens should it have? Well, we've just learned about the general formula. So 3 times 2 is 6, plus 2 is 8. So it should have 8 carbon atoms. So a little tutorial here. Here they're reminding you again of your prefixes, and so therefore your names for your straight chain alkanes, different lengths, different numbers of carbons. You need to kind of memorize this. So now we're going to get some examples. CH4, 1 carbon. So the answer should be methane. 1 carbon, meth, it's an alkane. So we're going to check our answer. And that is correct. 10 carbons. Notice that the formula is still CnH2n plus 2. So this is 10 carbons, so this should be decane. 3 carbons, propane. So I encourage you to continue to do this on your own. 8 would be octane. It's a good, all of these sweat sites are good for review. 2 carbons, ethane. Okay. Non-ane for 9. 4 is butane. Now we can go to, so these are straight chains. So let's do alkyl groups, and that gets us into substituents. So here is a pentane chain, 1, 2, 3, 4, 5. I hope you can see that cursor moving, 1, 2, 3, 4, 5, with one carbon substituent on it. And we call that methyl, okay, because it has 1. Methane, and then this alkyl group becomes, if it's just a group bonded to, that's what we call a carbon group that's bonded to the long chain. We call it an alkyl group. And its name is going to be derived from the hydrocarbon it came from. So methane has 1 carbon, methyl is the substituent with 1 carbon. Here's a substituent, it has 2 carbons. It's not ethane because it's not, I don't have another hydrogen here, but it's still named based on ethane, so it would be ethyl. Okay. There's a special name for this substituent. It is called isopropyl. This is a very common, propyl would be 3 carbons in a row. This is, and I know that we said that the chain can be kinked, but the point of attachment, the important thing here is that the point of attachment for this hydrocarbon is not on the central, it's on the middle carbon. So that is why we call it isopropyl instead of propyl. If the point of attachment to the longer carbon chain was at the end, then it would be propyl. So this is isopropyl. This is called S-butyl. And really you just have to memorize these different types. There's an isobutyl and S-butyl. There's a sec-butyl. I believe sec-butyl is the same as S-butyl. If it were just straight chain, this would be normal, butyl. 4 carbons, but being the prefix or the base for 4 carbons. It's being attached at the end, so it's butyl. Or we'd call it an N-butyl to the N, indicating a straight chain. But the point of attachment on this butyl group is not at the end. It's on the second carbon. So you can kind of think that's what sec means, but it really has to do with the fact that this carbon right here is a secondary carbon. Carbons with 2 hydrogens are, or at the end, I'm sorry, with 3 hydrogens are primary carbons. Carbons with 1, with 2 or 3 are primary. These are primary. So this would be primary. So essentially 2 hydrogens. 1 hydrogen is secondary. So that's really where the S comes from, or the same, another way to name this is sec-butyl. If the carbon had no hydrogens on it, and this carries through many classes of organic compounds, then it's a tertiary. And we'll probably come to that. Here it is right here. This carbon has no hydrogens on it, so this is a tertiary carbon. If this molecule had an OH attached to that line, this would be called an alcohol, and this would be a tertiary alcohol based on the carbon that the OH is bonded to. So this is tertiary butyl. Neopentyl It's primary carbon attachment. Just another group that just need to make a list of these because they come up not really often. The isopropyl comes up a lot, so definitely write that one down, but here are some others. This is 4 carbons. The point of attachment is at the end, so it's not propyl or isopropyl because those involve, that would be 3. It's not N-butyl because it would be a straight chain 4 carbon compound. It's not sec-butyl or S-butyl because it's not a secondary carbon. This is a primary carbon, so it can't be S-butyl or sec-butyl. It's not T-butyl because this carbon is not a tertiary carbon. It's not neopentyl because it would have 5 carbons. This only has 4, so this must be isobutyl. Just by looks like we have a little bit, maybe that's the last question. So I would come back to this website, click on the alkyl groups, and write down the structure and the name for some of these alkyl groups, because then those are going to be the substituents. That's how you're going to name substituents. Now, IUPAC in organic chemistry stands for International Union of Pure and Applied Chemistry, and has rules for how to name. And so I just want you to be aware that this section is here. So if you need review, then this is a good place to go. What I'd like to do is some practice, because this website doesn't use the line drawings. I'm going to introduce those kind of as we go through this tutorial. So I've got 1, 2, 3, 4, 5. I can either draw it this way or I can draw it this way. I've got a 5 carbon chain. I've got a methyl group hanging off of that chain, whether you draw it like this, then here is your methyl group, or if I draw it like this, then here is the methyl group. It is not going to change the name. So the base of the name is pentane because of the 5 carbons, and it's all single bonds. Oops. Pentane. But I have to put in front, the prefix is the substituent. If I start numbering it from this end, then that substituent's on the 4th carbon. I want to start from the right-hand side so that it's on the 2nd carbon. So 2-methyl, telling me that the substituent only has 1 carbon and it's on the 2nd carbon of the longest chain. All right, so let's check our answer. Okay. Alrighty, well, that's not working. Not good. Now, what I'd like to do before we leave this spot, is to show you how this particular drawing could be turned into a line drawing so that we can use some of those other sites. All right, so I've got 1, 2, 3, 4, 5 in the longest chain. The way that these line drawings work is that at every point in the line drawing, there is a carbon atom. So 1, 2, that's 2, 3, 4, 5. And the reason we draw it this way is 1, to see the points, and also that is really and it also implies the geometry of each of those carbon atoms. It's about the right geometric angle. And then on the 2nd carbon, I'm just kind of retracing up, I have a methyl group. So that's what the line drawing for that molecule would look like, and it looks like that is the only one they're going to let us do. Okay, let's try it again. 2-methyl pentane. All right, not working, so we're going to go back to our PowerPoint. But there are some good things here. You've got the naming rules, you've got your alkyl groups, and then your straight chain alkane names to review from. Going back to our PowerPoint, let's go back to one of the other websites which use more line drawings, and let's see if we can't do some of those. All right, so here's one of the others. Now this one is a number of quizzes, and I believe quiz 1 will do for where we are now. So we'll try that one, and then we will go back to another one of the links to do some more practice. All right, so wow, this looks really, really complicated. So let's see if we can't figure this out. If I look at this line drawing, I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 in my longest chain. 1, 2, 3, 4, 5 would not be as long. So it should end in hex. So those are B and C as possibilities. All right. If I start counting my chain at this end, it'd be 1, 2, 3, 4, 5. So it'd be 3 and 5 for my substituents. If I start at this end, 1, 2, 3, 4. So the left-hand side gives me the smaller numbers for my substituents. So so this is the way it's going to work. This is my first carbon. Sorry. This is my first carbon. On my second carbon, I've got an iodo group or an iodine group. And on my fourth carbon, I've got 2 methyl groups. Only one carbon here. One here, one here. 1 point, 1 point. So that says methyl to me. Methyl versus iodo. Iodo comes first. So it should be 2 iodo, 4,4 dimethylhexane. That should be choice C. Let's check our answer. And that is correct. Notice that there's quizzes 2 and 3, but that's going to get out of alkanes. And we may come back to those later. So which of these is the 3-isopropyl 2,2,6-trimethylheptane? So you want to look for a longest chain of 7 carbons. That's what the hept means. So 1, 2, 3, 4, 5, 6, 7. That's a possibility. 1, 2, 3, 4, 5. So that top one is possibility 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I cannot rule any of these out that have, they're all heptane of some type, but I've got substituents. So I see that it says 2,2,6-trimethyl. So I need to find 3 methyl groups and an isopropyl group. Well, this group right here is the isopropyl, and I see it on all of them. So they all have the isopropyl. However, let's see if we can. So it says 3, 1, 2, 3. On carbon 2, there should be 2 methyl groups. So you see where it says 2, 2? So that rules out this one. This one's gone. This one also has, well, 1, 2, 3, sorry. On the second carbon here, I don't have this group, so this is ruled out as well. Let's come down here. 1, 2, 3. Again, you don't have the second methyl group that you need. So here we go. 1, 2, so 2, 2 dimethyl, 3 isopropyl, 4, 5, 6 methyl, again 7, my 7th carbon. So this is my answer. All right. All right, so crazy that you would even look at this and think about chemistry, but there is a carbon atom here, and here, and here, and here, and here. The hydrogens are not shown in these line diagrams, so this would be a 5-carbon compound, and I believe that 5-carbon compound would be neopentane. No, that's incorrect. All right, my bad. Neopentane would be the name of the alkyl group, but it would not be the name of the alkane. So, finding my longest chain, this is what I totally ignored all my rules. 1, 2, 3, or 1, 2, 3. So either way I do it, I am going to have, oh, need to take all that out. I am going to have on this molecule, where are we? I am going to have, if this is my longest chain right here, if this is my longest chain right here, then I've got a methyl and a methyl. So 2,2-dimethyl propane. 2, 2, 2, 2 dash dimethyl, no space, propane. All right? Don't panic. You can do this. Find your longest chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it doesn't matter how I number it, I'm going to get the same result. Let's use this as my longest chain. That means I've got an ethyl group here, 1 carbon, 2 carbons, and I've got a methyl group here. If I start counting from, if I start counting from this end, 1, 2, 3, 4, I'll have 3 and 4 as substituent numbers. If I start from this end, it'll be 1, 2, 3. So that's the way I want to go. And the ethyl comes first. So the ethyl group is on the 3rd carbon. So 3 ethyl, 3 and then dash, 2 methyl, 1, 2, 3, 4, 5 pentane. 1, 2, 3, 4, 5. Yay! All right, why don't you give it a try? Find your longest chain. It's pretty obvious. Looks like you have an ethyl and a methyl as well. All right, I'm assuming you paused and gave it a try. So we have 1, 2, 3, 4, 5, 6, 7, 8 is our longest chain. So it definitely isn't D or A, so it's B or C. If I start counting from this end, it's a 1, 2, 3. So it would be 3 ethyl, 2 methyl, 3 ethyl, 2 methyl, octane. And the ethyl has to come first. So C should be our answer. Yay! All right, you want to give this a try? That is the isopropyl substituent group. Let's see if numbering, it may be part of your longest chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Either way, there's a rule in organic chemistry that says it would be best if I didn't call this 1, 2, 3 isopropyl heptane. Is that even a 5 isopropyl heptane is an option, but that wouldn't be it because a better way to number it would be from this end. So it's moved away. So if you have a choice, all right, so longest chain. This one being the longest chain, it's the same length. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So they would be the same. But I'm picking the least branched substituent by doing it this way, so that now my substituent is here, an ethyl group, and a methyl group again. And obviously I want to start numbering from this end. 1, 2, 3. So it is 3 ethyl, 2 methyl, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 heptane. So 3 ethyl, 2 methyl, heptane. Build 5 ethyl, so here's my ethyl group right here, 2, 3, 4 trimethyl heptane. 2, 3, 4 trimethyl heptane. See, this group right here is going to end up being part of the longest chain. 2, 3, 4. Right now, you have a methyl group. Where are we? We have a methyl group right here. All right? So that'd be 1, 2, 3. So I'm thinking that this, oops, hold on, let me toggle out of pin. I think that this group right here, stop it, sorry. This group right here needs to go here. And then my longest chain is 1, 1, 1, 2, 3, 4, 5. Does that work? 1, 2, no, that doesn't work. So maybe I want this group, instead of being here, maybe I want, oops, maybe I want, let's reset. Maybe I want to put it here. So let's just look at that. And I start numbering it. Well, let's do it if I number it from here, then it's 1, 1, 2, 3, 4, and that doesn't work because then that doesn't give. I don't have isopropyl isn't one of my isn't part of my name. So I'm going to start numbering it either from here, 1, it won't matter, 2, 3. So 1, 2, 3, 4. So at carbon 2, sorry, this is 3, this is 4. This is carbon 1, 2, 3, 4. So I've got a methyl group at 2, 3, and 4. There we go, 2, 3, 4 trimethyl. And then the ethyl group goes, oops, on carbon 5. So that goes here. Yay! All right. Wrong. All right, here's our next question. We want to build 6 isopropyl 2, 3, 4, 5, 7 pentamethyl nonane. So this one I've had to do a little bit of thinking on. This is one of the problems is this. We've got 1, 2, 3, 4, 5, 6, 7. So we don't even have our longest chain. If I start here, it'll be the same. 1, 2, 3, 4, 5, 6, 7. So I need to get 2 more carbons on this molecule. So I'm going to put this 2 carbon group. Remember, 1, 1, 2. Reset. Okay, I want it here. So now 1, 2, 3, 4, 5, 6, 7, 8. I'm almost there. If I put this group here, and then here's how I'm going to count. 1, 2, 3, 4, 5, 6. 6 isopropyl. This is an isopropyl group right here. 7, 8, 9. So there's my longest chain right there. Now, if I start counting like I just said, 1, 2, 3, 4, 5, 6, 7, 8, 9. I already have a methyl group at carbons 1 and, I'm sorry, at 2 and at 3 and at 4. I'm missing the one at 5, but I've got one more to add, so that's what I'm going to do next. Is put that one there. And so now once again, counting 1, 1, 2, 3, 4, 5. Oops, I messed up. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got a methyl group at carbons 2, 3, 4, 5, and 7, just like it says, and an isopropyl group at carbon 6. So that should be my molecule. Yay! I've just got a few more. Hopefully you're getting the hang of this. Octane is how our name ends. So that means I want 8 carbon chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So by virtue of elimination, this one is gone. It is not an 8 carbon chain. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this one is a possibility. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This one is also out. 1, 2, 3, 4, 5, 6, 7, 8. So these two on the right are possibilities. But let me do this bottom one again. 1, 2, 3, 4, 5, 6, 7, 8. However, my two substituents are methyl groups on that chain. And I want a methyl group at carbon 2, but an ethyl group at carbon 3. So this one up here has the 8 chain deal. 1, 2, 3, 4, 5, 6, 7, 8. And at carbon 2, I have that methyl group, and at carbon 3, I have the ethyl group. So that's my choice. Reset, and yay! All right. Heptane, how many carbons? 7 would be correct. So let's eliminate based on the fact on carbon chains. 1, 2, 3, 4, 5, 6. This one is eliminated. 1, 2, 3, 4, 5, 6, 7. This one's a possibility. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this one is out. Down here, 1, 2, 3, 4, 5, 6, 7. However, 1, 2, 3, I've got 2 methyl groups at carbon 3, and it does not say 3,3-dimethyl. That's what it would be if it was this molecule on the lower right. 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, we eliminated that one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2. 1, 2. 1, 2, 3, 4, 5, 6. That gives me a 3, 6. Let's start counting from the opposite end. 1, 2, 3, 4, 5, 6, 7. 7 carbon chain with a methyl group at 2 and 5, which is a better name than starting at this end, and these two substituents would be 3 and 6. So let me reset. This is my answer. Yay! 2 more. All right, pentane is how it ends. Focus on the ending. 5 carbons. This looks like a lot more than 5 here. I see 1, 2, 3, 4, 5, 6. So this one's out. 1, 2, 3, 4, 5. It has 5, but I see 1 substituent, and we need 2 methyl groups. So this one's out as well. 1, 2, 3, out. So I think it's going to be this one. 1, 2, 3, 4, 5. Pentane. 2, 2, 1, 2. 2 methyl groups, both at carbon 2. So that's my answer. Reset since I pushed on it so many times. Yay, last one. Okay, cyclopropane is how it needs to end. So let's just go ahead and type that in. Whoa. Like all of the writing I've been doing. Cyclopropane. Now don't press enter because we need to put our substituents on. In cyclic hydrocarbons, it doesn't really matter which carbon you start numbering at. If we start here at this top carbon, so what we have are 2 methyls and an ethyl. The question is the numbering. So cyclopropane is our parent chain. I've got 2 methyl groups here and an ethyl group here. If I start here and call it 1, 2, 3, then I'll have a 1 and a 3. If I start here, I'll have a 1 and a 2. So I'm going to go with the 1 and the 2, and let's see if I'm right. So it is going to be, and the ethyl comes first, so it's going to be 2 ethyl. Remember, ethyl comes first becomes first because of the alphabetical. 2 ethyl dash, only use commas, like in the instance I'm going to use them right now, 1,1 dash dimethyl cyclopropane. Yay! These ones where you have to type the name in are really a lot more difficult because they are, you got to get it exactly right. All right, I just want to click on quiz 2 and quiz 3 just to see what they're about, and then we might, come back to them later. You ought to be able to do this one, 2, 3. So the first 2, you have some cyclic, so why don't you give those a try? And then 3, it looks like 3, 4, we're going to be getting into maybe some alkanes, some aromatics. We're not quite ready for those yet, so we'll come back to this, okay, later, and remember that it's here. And then quiz 3 is even more advanced types of things, and we'll come back as we get into more organic chemistry later. So for now, quiz 1 goes with this organic 1 lecture. All right, let's go back to our PowerPoint. And we've done a bit of practice. I've shown you some tutorials. So let me go ahead and play my slideshow from here and finish this off. Reactions of alkanes. Alkanes are pretty unreactive due to the presence only of those carbon-carbon and carbon-hydrogen sigma bonds. Therefore, they make great nonpolar solvents. Remember, I used that word nonpolar earlier to describe anything with a, when it's just got these types of bonds, it is going to be nonpolar. The difference in electronegativity here is 0, very nonpolar. The difference in electronegativity here is 0.4, which for most practical purposes, and especially in a tetrahedral arrangement, that little bit of polarity will cancel out. So these are very nonpolar molecules. Gasoline is an example, and gasoline is very nonpolar. Unfortunately for students in the lab, with the exception of vegetable oil, which is kind of gross to work with, right, and clean up afterwards, many of your other organic non-polar solvents are kind of, bad to work with, like gasoline. Your hydrocarbons like hexanes and pentanes. You can use those, but they're flammable. They go into the gas phase very easily because they have the very small attraction between particles, and therefore they're just kind of hazardous to work with. So students don't get a whole lot of chance to work with nonpolar solvents in the lab. That can't be the end, but maybe it is. That is the end. The only type of reaction that you will get, let me go back to that last slide. The only type of reaction that you generally get from alkanes is combustion reaction. So let me just write that to finish us off. Of course, any hydrocarbon, when it reacts with, and it can contain oxygen as well. So I'll put that kind of in parentheses. That's certainly not the case with alkanes. And you put those with oxygen, you're going to get some CO2 and water, our basic hydrocarbon combustion reaction. Of course, however many carbons you have here is how many carbon dioxides, and however many Y's here, it'll be Y divided by 2. So if Y is 8, then you'll put a 4 here to balance. And then, of course, the oxygens are done by adding them up on this side, and then all you have to do is put something here. If it were something like glucose, C6H12O6 plus oxygen, then always save your oxygens for last, but the same kind of idea goes. 6 here, so 6 CO2s, water, 6 waters, and then your number of oxygens, 6 plus 12 is 18 on this side. I already have 6, so I need 12 more, so I will be putting a 6 here. All right, so that's basically your alkane reaction. If you were to take organic chemistry later, they'd talk about free radical reactions with alkanes, but we're just not going there because we're not going to do that much organic chemistry.